In the LLM era, detecting an object in an image isn't exactly impressive. Anyhow, this model does it. But what if I told you the same thing in real time, running across thousands of cameras simultaneously, every single one of them in real US high schools and hospitals? That's not a demo, that's a live system we've built. So, why not just throw an LLM at it? They handle images now. One image costs a little over a cent with Cloud Opus. 10 cameras, 2 frames a second. In 2 hours, we spent over $2,000. Those same $2,000 buy the hardware that ran our detection model for years for those same 10 cameras. LLMs aren't just the right tool here. My name is Yu from Gradient Insight, and this is the project we've done for angel protection, weapon detection across thousands of cameras running right now. This video is for anyone who needs to understand what it actually costs to run AI across real infrastructure, the architecture trade-offs, the hardware decisions, and why the obvious answer is usually wrong. I'm going to walk you through the 3 decisions that made this possible: edge over cloud, distributed over monolithic, fine-tune over pre-train, and why one of them cut the hardware costs by 90%, and the third one is the one where we spend the most time because it's the one that actually determines whether the whole thing works. When Angel Protection first came to us, they already had a system in mind. Cameras at each location feeding a local server. That server runs the model, detections, go to the cloud for the 911 alerts. Their instinct was to keep the footage local. The question they were really asking is, does it still hold at scale, or do we need to move the processing to the cloud? The cloud had a genuine case: elastic scaling, less hardware to manage on site, push model updates without touching the physical machines. For a lot of systems, cloud is the right call. But Angel Protection were already asking the right question. So we worked the numbers with them. One 1080p frame is around 1.9 megabytes. 100 cameras at 2 frames a second, that is 380 megabytes per second, continuously for every location. These are schools and hospitals. Most of them don't have this type of connection. And where they do, they are still competing with everything else on the network. That number settled it. Edge processing means that you only send alerts, not footage. The bandwidth requirement basically disappears. Latency and privacy just confirm what the bandwidth number already decided. Cloud inference adds a full network round trip on top of the model processing, and when you are detecting weapons in school corridors, that round trip adds real seconds. And raw CCTV footage of people is legally sensitive. On the edge, it never leaves the building. Only a timestamp and a cropped image goes anywhere. Angel Protection instinct was right. Edge won over every factor that actually mattered for their deployment. That settled the architecture, but knowing where to run it and actually building are 2 different problems. And when we ran the first version, something on the profiling data nearly changed everything. Now we know where it runs. We could build a system. After everything was running, something unexpected showed up. The first version was 1 machine per location, CPU and GPU at the same box, handling everything, decoding the streams, running the motion detection, running the model. 1 box, all in. And we've used the motion detection as a filter. Rather than running the model on every frame, the system first checked whether anything had actually moved, and skipped it if not. Most of the time the corridor is empty, so most frames never reach the model. But running that check across thousands of cameras every second is constant CPU work. And decoding that raw video stream sits on top of that. The CPU never got a break. Looking at the usage, the CPU was nearly at 100%, and the GPU was below 25%. The most expensive component in your whole setup, and it's basically idle. You're paying GPU prices, and the GPU is barely working. Clearly, there was room for improvement. But we were already on a high-spec CPU, so scaling up wasn't the answer. Having the most expensive part of your system sitting underutilized at this scale made the whole project much more expensive than it needed to be. So we changed the shape of the system entirely. Instead of one powerful machine doing everything, we split the work. Lots of small, cheap CPU-only machines. Each one handles a batch of cameras, decodes the streams, runs the motion detection, and only passes the frames with the actual movement to the GPU machine. The GPU's only job is the model. Because the GPU machine could now handle far more cameras and the CPU nodes are cheap commodity hardware, the total hardware cost dropped to 1/10 of what it started with. That is 90% hardware cost reduction. Not from a better model or a smarter cloud setup, from deciding that decoding and inference shouldn't live on the same machine. And that change is what made the business much more profitable. A brilliant architecture means nothing if the model gets it wrong. And this is the part most people underestimate. The model basically gets an image and tells you if there are any objects that you are looking for. In this case, weapons. The assumption is grab something pre-trained on a standard dataset like Coco or Open Images, point it at the feet, and you're done. These datasets are the foundation most object detection models are trained on. Coco alone has over 100,000 images covering 80 everyday categories like people, car, chairs, dog, laptops. Open Images goes even wider. For a lot of objects, that actually works, but we need to detect weapons in CCTV footage specifically, and that's where we found two issues to address. The first one, perspective. CCTV cameras are mounted up high, looking down. Most of the handgun images in the public datasets are side-ons, news photography, crime dramas, close-up shots. The model has generally never seen a gun from above at a distance in a grainy corridor at 2 a.m. The second one, size. At that distance, the weapon might be 30 pixels wide. Detecting something that small, reliable, under real conditions, those models were never trained for that. So we fine-tune. This simply means that we take a model that has already been trained on a big data set, which helps it understand the world. Then you train it with enough examples with the specific thing that you are trying to detect in the specific conditions that it will see in production, and it learns. We built our own dataset. CCTV angle images annotated tightly, trained on top of a strong pre-trained base. There are many places to find images, like other datasets, social media, even YouTube. Before we could train, we had to annotate, drawing bounding boxes around every weapon in every image. That sounds like tedious work, but it's actually crucial. Drawing them too loose or miss a few entirely, and the model learns to be just as imprecise. Around 1500 images per class before fine-tuning is a good starting point, but the quality matters more than the quantity. We ended up going deep enough into this that we ended up implementing YOLO v10 from scratch in PyTorch. The client let us open source it, and it's called Angel CV. It has a license of Apache 2.0, so you can use it commercially for free. And it's got sensible defaults, so you don't need to touch the configuration. But the open source was just a side effect. The actual goal was a model that works on a 2 a.m. corridor, picking out something the size of a postage stamp in a grainy top-down fit. And it does work. 3 decisions that made all the difference. Keep the footage on the edge so it never leaves the building, distribute the processing so the hardware cost drops by 10x, and fine-tune the model for how the cameras actually see, not how a benchmark dataset was put together. The result is end-to-end latency in the hundreds of milliseconds over 1,000 cameras across tens of locations, US high schools and hospitals, live right now. Edge over cloud, distributed over monolithic, fine-tuned over pre-trained. None of those were the default answers. They only make sense when you look closely at what are the actual constraints. That's what custom design gives you. If you are looking for something similar, security, manufacturing, anywhere where there are cameras already running and you are not doing anything useful with what they see, this is the kind of project we take on at Gradient Insight, and there's a free consultation link in the description below if you want to talk through what it might look for you. Until the next one.